Imagine this: you step outside on a quiet night, and above you stretches a canvas of endless stars. Some glow faintly, some blaze with fire, but together they whisper the same question humanity has asked for thousands of years. Where did all of this come from? Or has the universe always existed, stretching back into an infinite past beyond our imagination? This single question, the origin of the universe, has been at the heart of science, philosophy, and spirituality for centuries. Entire civilizations have crafted myths and stories to explain it. Priests, philosophers, and physicists alike have looked to the skies, searching for clues. And today, with powerful telescopes and deep scientific theories, we stand closer than ever to unlocking this grand mystery. But here's the twist: every answer we uncover only seems to open up even deeper questions. In this video, we'll embark on a journey across time itself. Together, we'll explore ancient myths and how they shaped humanity's first ideas of creation. We'll dive into the breathtaking theory of the Big Bang, where the universe burst into being from a single point of unimaginable energy. We'll uncover the strange role of cosmic inflation, the mysterious quantum ripples that seeded galaxies, and the faint afterglow of creation still shining in the night sky. But we won't stop there. Beyond the Big Bang, scientists are asking even more daring questions. Could our universe be just one bubble in a vast multiverse? What role might dark matter and dark energy have played in shaping the cosmos? And ultimately, what does it all mean for us, for life, for existence, for the mystery of why there is something rather than nothing? By the end of this journey, you may not hold all the answers, but you will carry a new sense of wonder about the universe we call home. And maybe, just maybe, you'll see the night sky differently the next time you look up. So, if you've ever felt that pull of curiosity when staring into the stars, if you've ever wanted to go beyond the surface of science and step into the deeper mysteries, then you're in the right place. Welcome to the Midnight Universe channel, where we explore the questions that keep us awake at night, the mysteries that spark wonder, and the science that takes us closer to truth. Take a moment now to subscribe, because what we're about to explore will change the way you see everything. From the smallest particle to the universe itself. The story of how the universe began is not just a scientific quest, it is the ultimate human story. And tonight, we begin humanity's first questions, before telescopes, before equations, before the word universe even existed. Humans looked up at the stars and felt the same burning curiosity you and I feel today. What are those lights? Where did they come from? And most haunting of all, how did everything begin? The truth is, long before science, the night sky was humanity's first teacher. And across cultures, our ancestors wove stories, myths, and philosophies to explain creation. These weren't just bedtime tales, they were survival, identity, and meaning wrapped into cosmic poetry. The first myths of creation in Mesopotamia, one of the world's oldest civilizations. Creation was told through a cosmic battle. The god Marduk split the body of a primordial chaos dragon, Tiamat, and from her remains shaped the heavens and the earth. Creation here was violent. Dramatic order wrestled out of chaos. Travel east to ancient India, and you find one of the oldest known texts, whispering about a time before time, a vast ocean of darkness. when there was neither being nor non-being. From that void, a primordial seed of creation expanded outward, not too far from what modern science would one day call the Big Bang. In ancient Egypt, creation was imagined as a cosmic egg hatching into the first gods, or as the primeval waters, giving rise to the sun god Ra. In Greek mythology, there was chaos, the great nothingness, out of which came Gaia, the earth, and Uranus, the sky, and far across the ocean. The Mayans imagined the gods gathered in the blackness before dawn, deciding how to bring forth the earth, the sky, and eventually humans, despite their differences. These myths share a striking theme. They all begin with nothing, darkness, chaos, water, or void, and then something emerges: light, sky, earth, the first spark of order. Humanity's earliest intuitions were already circling the idea that our universe had a beginning. From myth to philosophy, as civilizations matured, thinkers began to ask, could the universe have a natural explanation instead of only a divine one? The ancient Greek philosopher Aristotle argued that the universe was eternal, without beginning or end. To him, the cosmos simply was, existing forever as an unchanging whole. This idea, the eternal universe, would echo for centuries, but others disagreed. In the 6th century BCE, the philosopher Anaximander proposed that all things emerged from a boundless, undefined origin he called the Apeiron. Heraclitus, meanwhile, imagined the cosmos as a constant cycle of fire, eternal, yet always changing. These early thinkers planted the seeds of a transition from myth to philosophy, from divine battles to natural processes, the birth of scientific curiosity. Fast forward to the Islamic Golden Age and medieval Europe. Scholars preserved and expanded Greek ideas while weaving them with their own. The Persian scholar Al-Biruni measured the Earth's circumference with incredible accuracy, hinting at a universe governed by mathematics. Meanwhile, theologians wrestled with a deep paradox. If God created the universe, what existed before creation itself? Centuries later, the Renaissance would ignite a revolution. Copernicus dethroned Earth as the center of the cosmos. Galileo, with his telescope, revealed moons circling Jupiter, proof that the heavens were not perfect and unchanging. Kepler showed that planets followed precise mathematical laws, not divine whims. Newton unified it all with gravity, turning the universe into a vast machine governed by forces and equations. And yet, even as science advanced, one question remained untouchable. Did the universe itself have a beginning? The eternal universe debate for much of history. The idea of an eternal, unchanging cosmos held sway. To many thinkers, the idea of a beginning felt unsettling because a beginning implied something before, something beyond natural explanation. But whispers of a different possibility lingered, from myths of creation out of chaos to philosophies about cycles of birth and death. Humanity could never fully silence the thought that the universe had a first moment. This debate eternal cosmos, Ves created cosmos, would echo all the way into modern science. So, from dragon-slaying gods to the first philosophers, from cosmic eggs to eternal cycles, humanity's first questions were always the same. Where did it all come from? And just as myths gave way to philosophy, philosophy gave way to science. The mystery of origins would not stay in the realm of imagination forever. Because in the 20th century, scientists would discover evidence so powerful, so mind-bending, that it forever changed our understanding of the universe's beginning. That story begins with a single, explosive idea, the Big Bang. For thousands of years, humanity carried two competing visions of the cosmos, an eternal, unchanging universe versus a universe born from some primordial beginning. But in the 20th century, a few daring scientists and one stubborn priest set the stage for the most explosive idea in cosmology, that the universe had a birth. This was not just a theory. It was a revolution in how we see ourselves, our origins, and the very fabric of reality. The static universe that once was. By the early 1900s, most scientists still clung to the ancient belief in an eternal, unchanging cosmos. Even Albert Einstein shared this view. When he applied his newly minted equations of general relativity to the universe as a whole, he discovered something troubling. Gravity should cause the universe to contract. But Einstein couldn't accept a collapsing or expanding cosmos. To him, the universe must be static and eternal. So, he inserted a mathematical fudge factor into his equations, the cosmological constant, to balance gravity and keep the universe stable. It was a brilliant fix, except it was wrong. A Belgian priest with a big idea. Enter Georges Lemaître, a Belgian Catholic priest and physicist. In 1927, Lemaître took Einstein's equations seriously without the fudge factor and proposed something radical. The universe was expanding, but Lemaître went further. If the cosmos is expanding today, he reasoned, then in the distant past it must have been smaller, denser, and hotter. He imagined all matter and energy compressed into a single, primeval atoma cosmic seed that exploded outward in the moment of creation. This was the birth of what would later be called the Big Bang theory. Einstein dismissed it at a conference. He reportedly told Lemaître, "Your calculations are correct, but your physics is atrocious." But the universe itself was about to side with the priest. Hubble's telescope and the expanding universe at nearly the same time. American astronomer Edwin Hubble was using the Mount Wilson Observatory in California to study distant galaxies. Through painstaking observations, he made a discovery that shook science to its core. The light from these galaxies was stretched, shifted toward the red end of the spectrum. This redshift was a cosmic clue. It meant that galaxies weren't just sitting still, they were moving away from us. And not just a few galaxies. All galaxies, everywhere, were receding, as though space itself were stretching. In 1929, Hubble published his results. The universe was indeed expanding. Suddenly, Lemaître's radical idea didn't seem so crazy. If the cosmos was expanding now, then yes, rewind the tape of time far enough, and you arrive at a moment when everything was compressed into a single point. Einstein himself, upon visiting Hubble, was forced to admit defeat. He abandoned the cosmological constant, calling it the greatest blunder of his career. The name Big Bang and the ridicule, despite mounting evidence. The most prominent alternative was the steady-state theory proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi in 1948. In their view, the universe could expand forever without ever having a beginning, because as galaxies drifted apart, new matter was continuously created to fill the gaps. The cosmos, they argued, always looked the same on the largest scales, no beginning, no end. Fred Hoyle, in a 1949 BBC radio broadcast, mocked Lemaitre's idea by calling it a Big Bang. The name was meant as ridicule, but the insult stuck. And today, it's the term we all use for decades. The debate raged: Big Bang versus steady state, the smoking gun, cosmic echoes. The turning point came in the mid-1960s, according to Big Bang theory. If the universe began in a hot, dense state, kind of afterglow of creation itself, in 1965, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon a strange, persistent noise while testing a Bell Labs antenna in New Jersey. No matter where they pointed the antenna, the noise wouldn't go away. At first, they thought it might be pigeon droppings inside the equipment, but after cleaning everything, the hiss remained. What they had accidentally discovered was the cosmic microwave background, CMB, the ancient afterglow of the Big Bang, stretched into microwave frequencies by billions of years of cosmic expansion. This was the smoking gun. The evidence was overwhelming. The Big Bang was no longer just a theory. It was reality. Penzias and Wilson won the Nobel Prize, and the steady state theory was effectively buried. The universe with a birthday for the first time in history. Science could say with confidence, the universe had a beginning. This was more than a scientific breakthrough. It was a philosophical and cultural shockwave. The idea that time, space, and matter all had an origin was unsettling, even to scientists. Because if the universe began, what caused that beginning? Was there something before? Or does the very word before lose its meaning when time itself is born? Questions that once belonged to myth and religion had now returned. Through the back door of science, the Big Bang theory changed everything. Suddenly, the universe was not was a dynamic story with a fiery opening chapter. But that was just the beginning. Because with every discovery, new mysteries appeared. If the universe began in a hot explosion, what exactly happened in those first few moments? And could we ever peek back far enough to glimpse the very instant of creation itself? To answer these questions, we must dive into the first moments after the Big Bang, a time so extreme, so alien, that our minds can barely imagine it. Section 4. The first moments after the Big Bang. 1,200 words when we say the universe began. With the Big Bang, it sounds almost simple. An explosion, a flash of light, and suddenly space, time, and stars. But the truth is stranger, more alien, and far more mysterious. To truly understand cosmic origins, we must journey back to the first instant, the first unimaginably tiny sliver of a second, the Planck time, the Planck era. The unknowable beginning physicists define the earliest moment of time we can meaningfully speak about as 10 seconds after the Big Bang. That's not a fraction of a second. It's a fraction of a fraction. A number so small the human mind can't grasp it. This is the Planck time. At that instant, the universe was smaller than an atom, hotter than a trillion suns, and denser than anything we can imagine. All the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces were thought to be united into one dot. And here lies the problem. Our current physics breaks down at this scale. Quantum mechanics and general relativity, our two greatest theories, contradict each other in this regime. we don't yet have a working theory of everything that unifies them. So the very first moment of existence remains hidden from us, wrapped in mystery. But after that first tick of the cosmic clock, things become slightly clearer. The inflationary epoch, a universe in hyperdrive, out 10 raised to power minus 36 seconds after the Big Bang. The universe did something truly bizarre. Instead of just expanding, it underwent a sudden, violent surge called cosmic inflation. In less time than it takes light to cross a single atom, the universe expanded by a factor of at least 10. To put that in perspective, if a marble inflated by the same factor, it would become larger than the observable universe. Why inflation happened is still debated. Some physicists believe it was driven by a strange energy field, nicknamed the inflatone. Others suggest it was a quantum fluctuation that ballooned uncontrollably. Horizon problem. The universe looks the same in every direction, as if distant regions had once communicated. Inflation explains this, because those regions were once very close before inflation stretched them apart. The flatness problem. The universe today appears astonishingly flat, balanced between collapsing in on itself and expanding forever. Inflation stretched space so much that any curvature became smoothed out, like blowing up a balloon until its surface looks flat. Inflation was the universe's Big Bang within the Big Bang, and it set the stage for everything that followed. The quark-gluon soup, a primordial inferno. Inflation ended. The universe kept expanding and cooling. By the time it reached 10 seconds, it was still a furnace of unimaginable heat around 1 trillion degrees. At this stage, the universe was filled with a strange plasma called the quark-gluon soup. Quarks are the fundamental building blocks of matter, while gluons are the glue that binds them together. Today, they form protons and neutrons inside atoms. But in the early universe, the temperature was so extreme that quarks and gluons roamed free, swirling chaotically in a dense plasma. As the universe cooled further, quarks began to lock together, forming the first protons and neutrons, the building blocks of atomic nuclei. Matter versus antimatter. The great cosmic duel, one of the most profound mysteries of the early universe, is the battle between matter and antimatter. According to our best theories, the Big Bang should have created equal amounts of both. But matter and antimatter are enemies. Whenever they collide, they annihilate each other in a burst of pure energy. If they had truly been equal, the universe should have ended in a flash of radiation, leaving nothing behind. Yet here we are. Somehow, for every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny imbalance, just one extra particle per billion, was enough to tip the scales. The antimatter vanished in mutual annihilation, and the leftover matter became the stars, planets, and galaxies we see today. Why the universe favored matter over antimatter remains a great mystery. Some suspect subtle violations of symmetry in particle physics. Others hint at unknown laws. Whatever the reason, that tiny imbalance is why we exist. The first nuclei, cosmic alchemy, begins by about 3 minutes after the Big Bang. The universe had cooled enough for protons and neutrons to fuse together in the first act of cosmic alchemy, nucleosynthesis. In this brief window, The universe forged the first light elements, mostly hydrogen and helium, with trace amounts of lithium. These simple ingredients became the raw material for all future stars. Heavier elements, like carbon, oxygen, and iron, wouldn't appear until much later, forged inside the hearts of stars and released in supernova explosions. But those first nuclei were the seeds of cosmic chemistry. The Dark Age, a universe without light after nucleosynthesis. The universe entered a long, dark chapter. At around 380,000 years after the Big Bang, the temperature finally dropped enough for electrons to combine with nuclei, forming neutral atoms. This process, called recombination, allowed light to travel freely for the first time. That ancient light is what we now observe as the cosmic microwave. Background, CMB, a faint afterglow still bathing the universe. But here's the catch. Even though photons were free, the universe had no stars yet. For hundreds of millions of years, it remained a dark, featureless expanse, filled with invisible clouds of hydrogen and helium. Astronomers called this the cosmic dark age. Only when gravity slowly pulled matter together did the first stars ignite, ending the darkness and beginning the cosmic dawn. The poetry of first moments. Pause and consider this. In less than a second, the universe went from an unknowable quantum foam to an expanding fireball, to a soup of quarks and gluons, to the building blocks of matter itself. Within minutes, the recipe for stars was already written. These first moments hold the keys to understanding everything that followed, and yet they remain partly hidden from us, like a veil across the face of creation. Because behind every answer, a deeper question waits. What triggered inflation? Why did matter win over antimatter? And most haunting of all, what happened before the Planck time? Did time itself have a beginning, or is there something beyond the Big Bang? We have traced the story of the first moments, from unknowable origins to inflation, to quark soup, to the first atoms. But this is only the foundation. The next stage of our journey is the birth of structure, how those first atoms, under the layer of wonder, how the universe transformed from chaos into order, from fire into form, and from darkness into light. The early universe was silent, dark, and formless. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, no light, just endless oceans of hydrogen and helium, gas stretching in all directions, threaded with invisible strands of dark matter. This period, called the Cosmic Dark Ages, might seem empty, but hidden in that quiet darkness were the seeds of everything to come. Gravity, patient and relentless, was at work. Slowly, it began gathering matter into clumps, weaving the first scaffolding of the cosmos. Out of the silence, the first lights were about to be born. The role of dark matter, the invisible architect. One of the great mysteries of the universe is dark matter, a substance that neither emits nor absorbs light, yet outweighs ordinary matter 5-1. Though invisible, its gravity shaped the early universe. After the Big Bang, dark matter began collapsing into dense halos, forming invisible skeletons around which ordinary matter could gather. Without dark matter, gas would have spread too thin to form stars or galaxies. With it, the stage was set for cosmic architecture. Think of dark matter as the hidden framework of a cathedral. You may not see the beams holding it together, but without them, no walls could rise, no towers could reach upward. The universe's vast structure is built upon this unseen foundation. The first stars. Cosmic dawn, around 100 to 200 million years after the Big Bang. Gravity had compressed hydrogen and helium into the first giant clouds, dense enough to ignite. In their cores, nuclear fusion began, and the universe's first stars were born. These were not stars like our sun. They were population 3 stars immense, short-lived giants, often hundreds of times more massive than the sun. Their brilliance pierced the cosmic darkness, ending the dark ages in what astronomers call the cosmic dawn. These stars burned hot and fierce, living fast and dying young. In just a few million years, they exploded as supernova, scattering the first heavy elements: carbon, oxygen, iron into space. In their fiery deaths, they seeded the universe with the ingredients for future stars, planets, and life. The reionization of the universe, clearing the fog when the first stars lit up. The universe wasn't instantly transparent. It was filled with neutral hydrogen gas, which absorbed and scattered light. But the intense ultraviolet radiation from the first stars and galaxies began ionizing that gas, stripping electrons from atoms and clearing the fog. This process, called cosmic reionization, happened between 400 million and 1 billion years after the Big Bang. It was like the universe lifting its first veil, becoming transparent and visible across cosmic distances. Today, astronomers study this era by looking deep into space. The light from galaxies more than 13 billion years old shows us the universe in this transformative phase, when it was just beginning to glow with the light of countless suns. The birth of galaxies, islands of stars, stars gathered in clusters. Gravity bound them together into the first galaxies. These were small, irregular collections of stars, tiny compared to the massive spirals and ellipticals we see today. Over billions of years, galaxies merged and grew, colliding in titanic dances of gravity. Some became elegant spirals, like our Milky Way, with graceful arms winding outward. Others became giant ellipticals, vast spheres of stars. Galaxies became the great islands of light in the cosmic ocean, each containing billions or even trillions of stars. And within their swirling disks, new generations of stars continued to form. The cosmic web, the universe's grand design. On even larger scales, matter didn't form randomly. Guided by the pull of dark matter, it wove itself into an intricate cosmic web, vast filaments stretching across hundreds of millions of light years, with galaxies strung along them like pearls on a thread. Between these filaments lie enormous voids, regions almost empty of galaxies. This pattern of filaments and voids is the universe's largest structure, a grand architecture shaped by the invisible hand of dark matter and the relentless tug of gravity seen from afar. The cosmic web resembles a vast neural network, as if the universe itself were a kind of mind, with galaxies acting as its sparks of thought. The Milky Way's beginnings, our own galaxy. The Milky Way began as one of those small, irregular star clusters, nearly 13 billion years ago. Over time, it grew through mergers and collisions with smaller galaxies, slowly building the majestic spiral we see today in its center. A supermassive black hole formed, anchoring the galaxy's heart. Around it, billions of stars spun in a flat disk, while countless more filled its halo. The Milky Way is still growing. Even now, it pulls in dwarf galaxies, adding their stars to its vast collection. And billions of years from now, it will collide with its nearest large neighbor, the Andromeda Galaxy, merging into a new, even grander cosmic structure. The star factories, nurseries of light stars, are born in nebulae, enormous clouds of gas and dust. Gravity pulls the material inward, compressing it until nuclear fusion ignites. Each new star is like a spark struck in the dark, a small piece of the universe waking up. Stars live according to their mass. Smaller stars burn slowly, living for tens of billions of years. Larger stars burn hot and die quickly, exploding in brilliant supernovae that scatter heavy elements into space. This cycle of birth and death turned the universe into a chemical workshop. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in the hearts of stars and released in their deaths. We are, quite literally, made of stardust. From chaos to order, the emergence of structure. What makes this chapter of cosmic history so remarkable is the transformation from chaos to order. The early universe was nearly uniform, with only tiny fluctuations in density. But those small ripples, amplified by gravity, grew into the vast structures we see today. From random quantum fluctuations in the first instant of time, the universe gave rise to galaxies, stars, and planets, a grand order arising from the smallest seeds of chaos, the poetry of light returning. Imagine the silence of the cosmic dark ages. No stars, no galaxies, no light, only endless night. Then, slowly, one by one, the first stars ignite. Their light cuts across the void, reflecting off clouds of hydrogen, turning the darkness into a canvas of fire. It is one of the most poetic moments in cosmic history, the universe opening its eyes for the first time, with stars and galaxies formed. The universe had moved beyond darkness into light. The great cosmic structures were set, and the chemical ingredients for life had been created in the hearts of dying stars. But the story of the cosmos is not only about stars and galaxies. It is also about something much stranger, the invisible forces shaping its destiny. In the next section, we explore dark matter and dark energy, the hidden powers that drive the universe's past, present, and future. Asterisk, for centuries, humanity believed the universe was made only of what we could see: stars, planets, gas, dust. But modern science has revealed a startling truth. Everything visible, from galaxies to human beings, makes up less than 5% of the cosmos. The rest is hidden. Roughly 27% is dark matter, and an even larger 68% is dark energy, a force stranger than anything we can imagine. Together, these unseen players govern the universe's structure, its expansion, and its ultimate fate. We live in a universe where the invisible outweighs the visible. Dark matter, the cosmic gluing imagine throwing stars, gas, and dust into space. Without glue to hold them together, galaxies would fly apart, stars would drift away. Yet galaxies exist, and they spin with remarkable stability. What holds them together is not what we see, but what we cannot see: dark matter. Astronomers discovered dark matter in the 20th century while studying how galaxies rotate. The stars on the outer edges spun far too quickly to be held by the gravity of visible matter alone. Something unseen had to provide the extra pull. That unseen substance was named dark matter. Dark matter does not emit light. It does not absorb light. It passes through ordinary matter, almost like a ghost. Yet its gravity is undeniable, surrounds galaxies in vast halos, binding them together and shaping their evolution. Without dark matter, no galaxies would exist, no stars, no planets, and no us. What is dark matter made of? Here lies the mystery. No one knows what dark matter truly is. It could be exotic particles that barely interact with ordinary matter. It could be something entirely outside our current physics. Some theories suggest WIMPs, weakly interacting massive particles, invisible, heavy particles, drifting through the universe. Others propose ixions, feather-light particles that could fill all of space. Still others imagine dark matter as something even stranger, like hidden dimensions or primordial black holes left over from the Big Bang. Despite decades of searching through underground detectors, particle accelerators, and cosmic observations, we have not directly seen a single particle of dark matter. Yet its fingerprint is everywhere in the cosmos. The role of dark matter. In structure formation, dark matter is not just a background player. It is the cosmic architect. After the Big Bang, dark matter began collapsing under gravity, forming invisible scaffolds, where it condensed into stars and galaxies. In this way, dark matter determined where galaxies formed, how they clustered, and how the cosmic web stretched across space. It is as though the visible universe is a delicate frosting draped across the invisible skeleton of dark matter. Dark energy, the great cosmic repulsion. If dark matter pulls the universe together, dark energy pushes it apart. In the 1990s, astronomers studying distant supernova made a shocking discovery. The universe's expansion is accelerating. Instead of slowing down, as gravity should cause, galaxies are speeding away from each other faster and faster. The force driving this acceleration is called dark energy. Unlike matter, it is not localized. It fills all of space evenly. The more space expands, the more dark energy exists, fueling even faster expansion. Think of it like stretching a rubber band. Instead of getting weaker as it stretches, dark energy grows stronger, pulling the universe apart with increasing speed. The nature of dark energy. What is dark energy? That is perhaps the greatest question in modern cosmology. One possibility is that it is the cosmological constant first proposed by Albert Einstein, a property of space itself. Even in a perfect vacuum, space may have an energy that drives expansion. Another possibility is that dark energy is a new dynamic field, sometimes called quintessence, which changes over time, and still others suggest our understanding of gravity itself might be incomplete, that dark energy may not exist at all. But instead, gravity behaves differently on cosmic scales than we expect. The battle between dark matter and dark energy, the history of the universe, can be seen as a cosmic tug-of-war between these two invisible forces. In the early universe, dark matter dominated, pulling matter into clumps that became stars and galaxies. In the modern universe, dark energy dominates, driving galaxies apart and accelerating cosmic expansion for billions of years. Dark matter built structure, while dark energy now threatens to scatter that structure into the void. The outcome of this struggle may decide the universe's fate. How do we know these invisible forces exist? It may seem strange to claim knowledge of things we cannot see, yet science detects them through their influence. Dark matter, we observe it through galactic rotation curves, gravitational lensing, where light bends around unseen mass, and the patterns of the cosmic microwave background. Dark energy, we infer it from the accelerated expansion of the universe, measured by distant supernova, galaxy surveys, and the large-scale geometry of the cosmos. Like footprints in snow, we do not see the walkers themselves, but the evidence of their passage is undeniable. The universe we cannot see. When you look at the night sky, remember, the stars you see are only the tiniest fraction of reality. Around each galaxy is a vast, invisible halo of dark matter. Between those galaxies, dark energy stretches the very fabric of space. We are shadows, living in a shadowed universe. Our existence made possible by forces forever hidden from sight. The fate of the cosmos. Dark energy's final word, the future, depends on dark energy. If its strength remains constant, the universe will expand forever. Stars will burn out, galaxies will fade, and all will drift into darkness, a heat death. If dark energy grows stronger over time, the expansion could accelerate so violently that galaxies, stars, and even atoms are torn apart in a big rip. Or perhaps dark energy may weaken, allowing gravity to halt expansion and collapse the universe into a big crunch, resetting cosmic history. We do not yet know which destiny awaits, but whatever the outcome, it will be written not in the light of stars, but in the darkness of invisible energy. A universe of mystery. The lesson of dark matter and dark energy is humbling. We live in a universe where the majority of reality lies beyond our senses, beyond our instruments, beyond even our current imagination. Yet, paradoxically, this hidden universe has shaped everything: the galaxies, the stars, the chemistry of life, and the fate of time itself. Now that we have explored the invisible skeleton and engine of the cosmos, we turn to a question much closer to home. How did stars give rise to planets, and how did those planets create the stage for life? In the next section, we journey into the birth of stars and planetary systems, where cosmic dust becomes suns, worlds, and eventually the cradle of living beings. When you look up at the night sky, you are gazing at billions of cosmic fires, each a star, each a story of creation. But where do these stars come from, and how do they give birth to the worlds that circle them? The universe, shaped by dark matter and energized by cosmic expansion, still needs luminous engines to sculpt complexity. Stars are those engines. They are the forges where the elements of life are born. Around them, swirls of dust and gas give rise to planets, moons, and eventually, the possibility of beings like us asking these questions. This is the tale of how matter turns into suns, and suns turn into worlds. From dust to light, the birth of a star. Stars are not eternal. They are born, they live, and they die. Their births begin in vast clouds of gas and dust, called nebulae. These nebulae are immense, sometimes stretching across hundreds of light years, containing enough material to create thousands of stars. Within them, gravity slowly pulls gas and dust together, forming dense knots. As these knots collapse, they heat up. The gas compresses tighter and tighter until the temperature at the core rises to millions of degrees. At that critical moment, a miracle of physics occurs. Nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing light and heat. A star is born. It is like striking a cosmic match in the darkness, igniting a flame that can burn for billions of years. The life cycle of stars. Not all stars are the same. Their lifespans and fates depend on their size. Small stars, like red dwarfs, burn slowly and can live for trillions of years. Medium stars, like our sun, burn steadily for about 10 billion years before expanding into red giants and then collapsing into white dwarfs. Massive stars live fast and die young, burning through their fuel in just a few million years. When they run out of fuel, they explode in supernova, scattering heavy elements across the cosmos and sometimes collapsing into neutron stars or black holes. It is in the fiery deaths of stars that many of the elements essential for life, carbon, oxygen, iron, are created and released into space. In this sense, every breath you take carries atoms forged in the heart of ancient stars. You are, quite literally, made of stardust. Protoplanetary disks, the cradle of worlds. When a star forms, it is often surrounded by a rotating disk of gas and dust. This is the protoplanetary disk, the birthplace of planets. Within this swirling disk, particles collide and stick together, forming clumps. Over millions of years, these clumps grow into planetesimals, mountain-sized bodies of rock and ice. Through further collisions and accretion, planetesimals merge into full-fledged planets, closer to the star, where it is hot. Rocky planets, like Earth and Mars, form. Farther out, where it is colder, gas giants, like Jupiter and Saturn, emerge, their cores pulling in thick envelopes of hydrogen and helium. This process is violent and chaotic. Entire worlds collide, some shattering, some merging. The scars of this era can still be seen today. Craters on the moon, tilted axes of planets, and asteroid belts left as cosmic debris. The role of supernova in planet formation. But where did the material for these planets come from? The answer lies in the life cycles of earlier generations of stars. When massive stars explode as supernova, they scatter heavy elements, carbon, silicon, iron, into space. These elements mix into gas clouds, enriching them. Thus, the nebulae that form new stars and planets are not made only of hydrogen and helium from the Big Bang. They also contain the ashes of ancient stars. Without supernova, there would be no rocky planets, no oceans, no life. Our very Earth is built from the remnants of stars that died long before the sun was born. Planetary diversity. Many kinds of worlds. The planets that form around stars are astonishingly diverse. Some are hot Jupiters, giant planets orbiting so close to their stars that their atmospheres boil. Others are super-Earths, rocky planets larger than our own, possibly with thick atmospheres and oceans. Still others may be ice worlds, shrouded in frozen shells, hiding liquid oceans beneath our own. Solar system is just one example of the variety possible. With thousands of exoplanets now discovered, we know that planetary systems are not rare, they are the rule. Almost every star may host its own retinue of worlds. the Goldilocks zone, a stage for life among all these planets. Some may lie in the habitable zone, the region around a star where conditions are just right for liquid water on Earth. This zone allowed oceans to form, creating a stable environment where life could emerge. For other planets, the habitable zone may hold equally promising conditions, but being in the habitable zone is not enough. Many other factors matter: planetary atmosphere, magnetic field, geological activity. The odds are slim, but given the vastness of the universe, they are not zero. Our solar system, a cosmic family. Let's return home for a moment. Our own solar system tells the story of planetary diversity vividly. The inner planets Mercury, Venus, Earth, Mars are small and rocky. The outer giants Jupiter, Saturn, Uranus, Neptune are massive and gaseous. Between them lies the asteroid belt, filled with leftovers from planet formation. Beyond Neptune, icy worlds like Pluto drift in the Kuiper belt. All of these worlds trace their origin to the Sun's protoplanetary disk 4.6 billion years ago. Earth itself is just one of countless outcomes in the cosmic lottery of planet formation. The fragile balance of creation, the birth of stars and planets, is a story of balance between chaos and order. Collisions, explosions, and collapse create structures of breathtaking stability, stars that burn for billions of years, planets that trace graceful orbits, moons that dance around their primaries. It is through this balance that the stage for life is set. For without stars, there is no light, no warmth, no chemistry. Without planets, there is no ground to walk upon, no seas to sail, no skies to breathe beneath. From stars to consciousness, here the story takes a profound turn. Out of hydrogen clouds come stars. Out of stars come elements. Out of elements come planets. And on at least one of those planets, matter became aware of itself. The chain from dust to light, from light to life, is not inevitable, but it happened here, and perhaps somewhere else it has happened too. Having seen how stars and planets are born, we are ready to ask the most profound question: how did life itself emerge from these worlds of rock and gas? From the ashes of stars and the dust of planets comes something far more mysterious: life. For billions of years, the universe was filled with galaxies, stars, and planets, but no voices, no thoughts, no awareness. Then, on at least one small, rocky planet orbiting an ordinary star, chemistry stirred into biology. Matter became alive. How did this extraordinary transition occur? The origins of life remain one of the most profound scientific mysteries. Yet, through research and imagination, we have begun to piece together the story. It is a tale of water, molecules, energy, and time. The early Earth, a planet of possibilities. 4.5 billion years ago, Earth was young, raw, and violent. Its surface boiled with volcanoes. Asteroids rained down from the sky. Lightning flashed through thick, toxic clouds. Oceans of molten rock cooled into seas of water and stone. But within this chaos lay the ingredients for life. The Earth's surface held carbon, hydrogen, nitrogen, and oxygen, the building blocks of organic chemistry. Energy from sunlight, lightning, and geothermal vents provided the sparks needed to drive chemical reactions. It was a planet in transition. but one perfectly suited for experimentation on a grand scale. The building blocks of life. All living things share certain molecules, DNA, proteins, lipids, and sugars. But these complex molecules must have started from simpler beginnings. Experiments like the famous Miller-Urey experiment in 1953 showed that when simple gases, methane, ammonia, hydrogen, and water vapor are exposed to electrical sparks, they can form amino acids, the raw ingredients of proteins in nature. Similar processes could have been happening for millions of years. Ultraviolet light from the sun, lightning strikes, and hydrothermal vents at the bottom of the ocean may have cooked up the first organic compounds, from molecules to self-replicators. But chemistry alone is not enough. Life requires molecules that can copy themselves, passing on information. One candidate is RNA. Unlike DNA, which is more stable, RNA can both store information and catalyze chemical reactions. Some scientists propose an RNA world hypothesis, that early life began with simple RNA molecules that could replicate and evolve. Over time, these molecules became more sophisticated, joining into networks of reactions that laid the foundation. For biology, the role of water was essential. It dissolved molecules, allowing them to interact and combine. It stabilized delicate structures, and it provided a medium where reactions could repeat endlessly. Without liquid water, life as we know it may never have formed. This is why scientists searching for alien life look first for signs of water on Mars, Europa, Enceladus, and distant exoplanets. On early Earth, oceans acted as vast laboratories, mixing ingredients over millions of years until something remarkable emerged. The first cells. At some point, molecules began to organize into protective bubbles. These primitive membranes, made of fatty acids, could trap useful molecules inside, shielding them from harsh conditions. Inside these bubbles, chemical reactions could run more efficiently, concentrating the raw materials of life. Eventually, these structures evolve into the first cells, tiny packages of organized chemistry. The leap from chemistry to biology was complete. The spark of evolution. Once cells existed, evolution took over. Random mutations created variety. Natural selection preserved the changes that worked best. Over immense spans of time, single-celled organisms grew more complex. They developed ways to harvest energy from sunlight through photosynthesis, filling the atmosphere with oxygen. This oxygen, once toxic, later became essential for the rise of complex animals. From microscopic beginnings, life began reshaping the planet itself. The panspermia hypothesis, seeds from the stars. While many scientists believe life originated on Earth, others suggest a cosmic possibility, panspermia. This idea proposes that life's building blocks, or even primitive microbes, may have come from space, carried on asteroids, comets, or interstellar dust. We know that amino acids and organic compounds exist on comets and meteorites. If they landed on early Earth, they could have enriched the chemical soup that gave rise to life. Whether life began here or arrived from the stars, the result is the same. A world alive with possibility. The great mystery. Why life? Even with these theories, the question remains, why should lifeless molecules assemble into living systems at all? Some scientists argue it is simply a matter of probability. Given enough time and enough experiments, chemistry will eventually stumble into biology. Others suggest deeper principles of physics, that the universe naturally tends toward complexity and organization under the right conditions. Whatever the explanation, life remains one of the universe's greatest miracles. The fragility and resilience of life. The earliest forms of life were fragile. A single change in environment could have wiped them out. Yet once life appeared, it proved astonishingly resilient. Microbes adapted to extreme heat, cold, pressure, and radiation. Even today, so-called extremophiles live in boiling vents, acidic lakes, and frozen tundrous environments once thought impossible for life. Their existence reminds us that the conditions for life may not be as rare as we once imagined. From chemistry to consciousness, the origins of life are not just a scientific puzzle. They are a philosophical one. At what point does chemistry become biology? At what point does biology become awareness? We know the chain. Stars forge elements, elements form planets, planets provide. Chemistry gives rise to life, but how life leads to thought, memory, and consciousness, that is the mystery still unfolding. Our place in the living universe. The story of life's origins is not only about the past, it is about us. Every cell in your body carries echoes of those first cells. Every breath you take depends on ancient processes like photosynthesis. You are a continuation of a chain that began billions of years ago in the quiet oceans of a young planet. You are living proof that the universe does not merely create stars and galaxies, it also creates beings who can wonder about them, having explored the beginnings of life. We now approach another leap in the cosmic story, the rise of intelligence and consciousness. For billions of years, life on Earth was simple. Tiny cells floated in oceans, eating, dividing, and evolving. Slowly, complexity increased. Organisms developed specialized parts, nervous systems, and eventually brains. And then, somewhere along the universe crossed a threshold. Matter began not only to live, but to think. From stardust and chemistry emerged conscious beings, capable of awareness, memory, imagination, and curiosity. The cosmos, once silent, now had voices. It could wonder about itself. From simple brains to complex minds, the first nervous systems appeared in tiny, soft-bodied creatures hundreds of millions of years ago. They were simple networks of cells that could detect light, movement, and touch enough to help an organism find food and avoid danger. Over time, evolution sculpted more complex systems. Fish developed spinal cords. Amphibians and reptiles built larger brains. Mammals gained sophisticated memory, emotions, and learning abilities. The brain became nature's masterpiece, a living computer with billions of neurons, each firing tiny electrical sparks in endless patterns. The leap to human intelligence. Among all species, humans represent a staggering leap. Roughly 2 to 3 million years ago, our early ancestors Homo habilis and later Homo erectus began crafting tools, controlling fire, and living in organized groups. But it was Homo sapiens, emerging about 300,000 years ago, that carried intelligence to its peak. Our brains, especially the prefrontal cortex, allowed us to plan, imagine, and create symbolic thought. We developed language, our most powerful tool. Through words, we could share knowledge across generations. Ideas no longer lived and died with individuals. They became immortal. Consciousness. The universe becomes aware. What exactly is consciousness? It is more than intelligence. Many animals are intelligent, but consciousness is the ability to experience, to feel the warmth of sunlight, to remember a childhood moment, to imagine a future that has not yet happened. Philosophers call this the hard problem of consciousness. How do electrical signals in the brain create subjective experience? Why does the firing of neurons feel like something? We do not yet know. Consciousness may be an emergent property of complexity, or it may hint at something deeper about the nature of reality itself. What we do know is that with consciousness, the universe achieved something astonishing. It could look back at itself. Through your awareness, the cosmos became self-aware. The role of curiosity intelligence alone is not enough. What makes human minds unique is curiosity. From the beginning, humans wondered, what are the stars? Where does the sun go at night? What happens after death? These questions drove us to create myths, stories, science, and philosophy. Curiosity fueled exploration. It carried our ancestors out of Africa, across continents, and eventually into space. It gave birth to art and technology. Without curiosity, intelligence would have remained silent. With it, we became explorers of both Earth and the cosmos. Language, memory, and culture. The human mind expanded not just through biology, but through culture. Language allowed us to pass on discoveries. Fire-making, hunting strategies, and medicine were preserved and improved. Memory became collective, stretching far beyond the lifespan of any individual. Over millennia, this collective memory built civilizations. It gave rise to writing, mathematics, and astronomy. Through stories and symbols, humans began mapping the universe in both mythic and scientific ways. Culture became our second inheritance, passed not through DNA, but through teaching, writing, and tradition. The cosmic significance of intelligence. Why should the universe produce beings capable of thought? Some scientists argue that intelligence is simply another evolutionary adaptation, like wings or claws. It helps us survive. But others see something deeper. Perhaps intelligence is the cosmos's way of knowing itself. Carl Sagan once said, "We are a way for the cosmos to know itself." Your mind, your thoughts, your memories, they are not separate from the universe. They are the universe, organized in such a way that it can reflect upon its own origins. The mystery of consciousness in other life forms. Humans are not alone in experiencing the world. Dolphins, elephants, ravens, and great apes show signs of complex thought. Octopuses demonstrate problem-solving skills. Dogs and cats clearly feel joy, fear, and love. Consciousness may not be unique to us. It may be a spectrum spread across many species. If so, then intelligence is not the crown of creation, but part of a larger web of awareness that stretches across the tree of life. Could consciousness exist beyond Earth? If life exists on other worlds, could it also evolve intelligence and consciousness? The same evolutionary pressures, finding food, avoiding predators, cooperating in groups might favor advanced brains. Alien civilizations could be out there thinking their own thoughts, asking their own questions about the stars. If so, then consciousness is not just an earthly phenomenon, it is a cosmic phenomenon. The universe may be filled with minds, each reflecting reality in different ways. The paradox of awareness yet consciousness also brings burden. To be aware is to know joy, but also suffering. To imagine the future is to imagine both hope and fear. Humans became aware not only of life, but of death. This realization shaped religion, philosophy, and art. Our awareness gave us beauty and creativity, but also anxiety and longing. It is the paradox of consciousness. The gift that makes life meaningful also makes it fragile. The dawn of artificial intelligence. Today, humanity stands at a new frontier. For the first time, intelligence is no longer limited to biology. Artificial intelligence machines, capable of learning and reasoning, has begun to emerge. Will AI ever achieve true consciousness, or will it remain a powerful tool without awareness? We do not yet know, but its existence forces us to ask, consciousness tied to biology, or can it arise wherever complexity allows? The cosmic chain of awakening. Looking back, we see the chain clearly. Stars forged elements, elements built planets, planets gave rise to life, life evolved into intelligence, intelligence blossomed into consciousness, and now consciousness creates stories like the one you are hearing now. To understand where it came from, the universe has not only created galaxies and stars, it has created minds that can dream of galaxies and stars. Transition to next section. And so we stand at the edge of another question. If intelligence and consciousness are the universe awakening, what comes next? In the final part of our journey, we will explore the future of the cosmos where science, imagination, and destiny converge. From the fate of galaxies to the ultimate question, what is the end game of existence? The story of the universe is vast, stretching from the birth of time to the rise of human consciousness. But no story is complete without its ending. What comes next? What is the destiny of the stars, of galaxies, of life itself? And what role do we teeny beings on a pale blue dot play in this unfolding drama? In this final chapter, we gaze forward into the future of the cosmos and confront the questions that lie beyond science, in the realm of philosophy, imagination, and wonder. The fate of the stars. Every star in the night sky is a furnace of nuclear fire. Yet even these brilliant giants have lifespans. The smallest red dwarfs will burn slowly for trillions of years, glowing faintly long after all other stars are gone. Larger stars, like our sun, shine for billions of years before expanding into red giants and eventually collapsing into white dwarfs, dim embers of their former selves. The most massive stars explode in supernovas, leaving behind neutron stars, or black holes. The universe's night sky is therefore not eternal. Slowly, stars will fade. The galaxies that now blaze with light will one day fall into darkness. The expanding universe. Since the Big Bang, the cosmos has been expanding. Not only are galaxies moving apart, but the very fabric of space is stretching. Scientists once thought gravity might slow this expansion, perhaps even pulling everything back together in a big crunch. But observations show the opposite. The universe's expansion is accelerating, driven by something mysterious, dark energy. If this continues, galaxies will drift further and further apart until distant stars vanish from view. Future civilizations, billions of years from now, may look at the night sky and see only darkness, unaware that a vast universe once existed, the long future, heat death, or something else. So what is the ultimate fate of the cosmos? There are a few possibilities. Heat death. If expansion continues forever, stars will burn out, black holes will evaporate, and energy will spread so thin that the universe reaches a state of maximum entropy, silent, cold, and dark. The Big Crunch. If gravity eventually overcomes dark energy, the universe could collapse inward, ending in a fiery implosion where time itself ends. The Big Rip. If dark energy grows stronger, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. Cyclic universes. Some theories suggest the universe may go through endless cycles of birth and death, big bangs followed by big crunches. The truth remains unknown. But whatever the ending, it will unfold on timescales so vast that human imagination struggles to grasp them, trillions of years or more. The role of life in the cosmic future. Yet the cosmos is not just drifting matter. It has produced life creatures capable of wonder. And perhaps life has a role in shaping the future. Humans are the first species we know of that can alter the destiny of their world. We have harnessed fire, built machines, and even launched probes beyond the solar system. In time, our descendants, or the life we create, may spread beyond Earth, carrying consciousness to the stars. Imagine civilizations among the galaxies, preserving knowledge long after Earth is gone. Imagine intelligence outliving the stars, themselves finding new ways to endure in a fading cosmos. The question of meaning, but beyond survival, lies a deeper question. Why? Why does the universe exist at all? Why is there something instead of nothing? Science explains the how, but not always the why. Perhaps there is no ultimate purpose, just a universe unfolding according to natural laws. Or perhaps purpose is not given from outside, but created from within. Meaning may be something we weave ourselves, like stories written against the backdrop of the stars. The possibility of multiverse universe may not be the only one. Some theories suggest that the Big Bang was just one of many, and that countless other universes exist, teach with different laws of physics, different histories, perhaps even different forms of life. If true, then the question of meaning becomes even stranger. We may live in one bubble among an infinite sea of universes, each with its own beginning and end. In such a multiverse, our existence may be both insignificant and miraculous, one tiny thread in an infinite tapestry. The human perspective. When we look at the stars, we see distances and times beyond comprehension. It is easy to feel small, and yet, in another sense, we are vast. The atoms in your body were forged in ancient stars. Your mind carries the memory of evolution, of countless generations. And through your awareness, the cosmos looks back upon itself. In a universe 13.8 billion years old, you are alive right now in this brief, luminous moment. That alone is extraordinary. Across history, humans have tried to make sense of the universe through stories, myths, religions, philosophies, and now science. Each story reflects our longing to connect with something greater. This video, this series, is another such story, a way to bring together the vastness of cosmology with the intimacy of human wonder. Science gives us facts, but it is storytelling that gives those facts meaning. And perhaps that is our gift, not just to survive, but to tell the story of the universe, to carry it forward, so it is not forgotten when the stars fade. The final questions. At the end of our journey, we arrive at questions that may never be fully answered. What sparked the Big Bang? Is our universe one of many? What is the true nature of consciousness? Does the universe have a purpose, or only the meaning we create? These questions may remain mysteries forever, or perhaps, in some far future, conscious beings will find answers. So, here we are, stardust that can dream. The universe began in a flash of light, expanded into galaxies, gave birth to stars and worlds, to life and thought. And now, through you, it reflects upon itself. Perhaps the cosmos does not need an ending. Perhaps its story is not about final answers, but about the questions themselves, the wonder that keeps us searching. As you close your eyes tonight, remember this: you are part of something vast, ancient, and ongoing. The story of the universe is also the story of you. And if this journey moved you, if you want to keep traveling with us into the mysteries of time and space, subscribe to the Midnight Universe, where the cosmos is never silent and the questions never end.